In part A, we're going to use the fact that the definition of the derivative, the limit definition, is the limit as h goes to 0 of f of x plus h minus f of x all over h. Plugging into the function 1 over x, we have the limit as h goes to 0 of, all right, in 1 over x, it'll be 1 over x plus h. Then we're subtracting the original function, which is subtracting 1 over x, and we're dividing this whole thing still by h. I think a good approach here is to cancel the fractions within fractions, which means I'm going to multiply by the least common denominator, which is x times x plus h, the product of the two denominators. I'm going to multiply that to every single term, essentially multiplying it to the numerator and the denominator. This is the limit as h goes to 0 of, so we have 1 over x plus h, and this is multiplied by x times x plus h. Then we subtract off 1 over x, again multiplied by x times x plus h. And in the denominator, we also have h times x plus h. So what cancels? The x plus h, over here the x, those denominators are now 1. What we have left over is the limit as h goes to 0 of, okay, here we just have x, so I'll put x. Then we have minus. Here it's just x plus h, being careful to keep the parentheses, so I'll put minus x plus h. And I'll write the denominator as, I guess, h times x plus h. Continuing, I see we can distribute the negative in the numerator and simplify, so I'll do that next. This is x minus h over h times x plus h, which is the limit as h goes to 0 of minus h over h times x plus h. I see that I can now cancel this h with that, leaving just 1 in the numerator. And so this is the limit as h goes to 0 of negative 1 over x times x plus h. I can now plug 0 in place of h because I have a defined value, and that is negative 1 over x times x plus 0, and that simplifies to negative 1 divided by x squared, and that is the derivative of 1 over x. In part B, we have a particle that is traveling along a horizontal line, and that's according to the position function t squared minus 4t. And for my picture, I'll have moving to the right in the positive direction and left as the negative direction. And we can see at s of 0, it starts at 0, so that's the starting point here. To find the total distance traveled, we have to consider if the particle changes directions at any point. This means we have to find the velocity of the particle, see when it is equal to 0, and then when it's negative and when it's positive. If you'd like to find the velocity of this particle, that's the derivative of this position function, which is 2t minus 4. So when is the velocity equal to 0? That is when 2t minus 4 is 0. Or simply, when t is equal to 2, in this case, that is in seconds. Now, if you graph this velocity function, v of t, at 0, it starts at negative 4, so that's here. It's equal to 0 at 2 seconds, and then it's positive. So here's my velocity function. This means if we are from 0 to 2, the velocity is negative, means we're going to the left. If we're after 2 seconds, the velocity is positive and we're going to the right. So I'll note that on this interval, the interval from 0 up to and not including 2, the particle is moving left. And this is because the velocity function is negative. At 2 seconds, it stops because the velocity is equal to 0. And then if we are greater than 2 seconds, it's moving right. And that's because the velocity is positive. If we put this all together, to find the total distance traveled, we're starting here. We're first going to see how far it travels to the left, and then to that, we're going to add how far it travels to the right. I'll let d1 equal the distance that we go left, and this is equal to the absolute value of s of 0 minus s of 2. If I plug these numbers into the function, s of 0 is 0 minus at 2, s of 2 is negative 4, and this is equal to the absolute value of 4, and that is equal to 4, and this is meters. If I want d2, which we'll say is the distance the particle moves to the right, this is equal to s of 2 minus, and we're going up to and including 5 seconds, s of 5. If we plug this into the function, again, s of 2 is negative 4, minus, if we put 5 into the function, we get 5. So this distance is negative 4 minus 5, which is negative 9, and that is positive 9 meters. We're running out of room, so I'll put the total distance over here. The total distance is going to be d1 plus d2. So I'll say total distance which is d1 plus d2, is equal to 4 plus 9, which is 13 meters. And that this is the answer to this part. In part C, we want to find the horizontal and vertical asymptotes of this function. To start with the horizontal asymptotes, I'll use limits. We're going to consider the limit as x approaches both positive and minus infinity of this function. For this rational equation, these limits will be the same, and they'll correspond to a horizontal asymptote. This is the limit as x approaches either positive or minus infinity of, our function is x squared plus 3x plus 1 all over 4x squared minus 9. And what I'll do is divide every single term by x squared. So this becomes the limit as x goes to either positive or negative infinity of, we get x squared divided by x squared plus 3x divided by x squared plus 1 divided by x squared. In the denominator, that's 4x squared divided by x squared minus 9 divided by x squared. If we simplify this expression, the top is 1 plus 3 over x plus 1 over x squared. In the denominator, we have 4 minus 9 over x squared. I think I'll note that this, and this all go to 0 because we have x's in the denominator. So to evaluate this limit, it's equal to 1 plus 0 plus 0 all over 4 minus 0, which is simply 1/4. And this means we have a horizontal asymptote on this equation of y is equal to 1/4. To find the vertical asymptotes of this function, I'm going to use a fact. I'm going to state it here. So the fact is, in a rational function, any x value in which the numerator is non-zero and the denominator is 0 is a location of a vertical asymptote. Now that we have this fact stated, what I'll do is look at the denominator of this function. I'll set it equal to 0 and solve for x. I'll check to see if those numbers make the numerator non-zero. If this is the case, This will mean that the two x values are the location of vertical asymptotes. So here's the denominator. It's 4x squared minus 9. I want to check to see where it's 0. That's where 4x squared is equal to 9. And that is where x squared is equal to 9/4. And that means x is equal to plus or minus the square root of 9/4, which is plus or minus 3/2. I will continue this work on the next slide. I'll state that these are two potential locations of a vertical asymptote. What we'll do is check just to make sure that those numbers don't make the numerator equal 0. All right, so do -3/2 and 3/2 make the numerator 0? I'll check this by simply plugging those numbers in. So let's see, if we check -3/2, we get this. And let's see, that's equal to positive 9/4 minus 9/2 plus 1, which is equal to, okay, so common denominator 4. That's 9 minus 18 plus 4 all over 4. That's -9 plus 4. That's -7/4. And all I care is that that's not 0. And this means that x equals -3/2 is a vertical asymptote. I'll also check x is equal to positive 3/2. All right, so there we have 3/2 squared plus 3 times 3/2 plus 1. I mean, there's no way this is going to be 0, but just to get a number for it, that's 9/4 9/2 plus 1, common denominator 4. So we get 9 plus 18 plus 4 all over 4, and that is equal to 31/4, but all I care is that it's not 0, and therefore x is equal to positive 3/2 is a vertical asymptote. So it turned out that both numbers that made the denominator 0 were vertical asymptotes. This isn't always the case. If these numbers either made this equal 0 or this equal 0, then potentially they might not be vertical asymptotes. Let's use L'Hopital's rule to evaluate this limit. The first thing to point out is that the numerator is going to positive infinity, and so is the denominator. This is of the form infinity over infinity, which means we can apply L'Hopital's rule. L'Hopital's rule says we can take the derivative of both the numerator and denominator separately and consider that new limit instead. So the derivative of the numerator is 2x, and the derivative of the denominator is -e to the 1 minus x. That's because the derivative of e to anything is e to that thing. The derivative of 1 minus x is -1, so I put the negative in front. Okay, so this new limit, can we compute it? I'm noticing that this is another indeterminate form. The numerator is going to negative infinity. The denominator is now going to negative infinity. This is another infinity over infinity, which means we can apply L'Hopital's rule yet again. So this is the limit. As x goes to negative infinity of 2, divided by, this will be e to the 1 minus x. What happened here is the derivative of this goes to e to the 1 minus x times -1. With this extra -1, they cancel to give us just this. Now, what does this limit equal, if anything? Well, 2 is now a constant. It's just a number. And the denominator is going to infinity. So this thing is of the form 2, a constant over infinity. Now, this is not an indeterminate form. This actually does equal something. This is equal to 0. Because this limit exists and is 0, it is equal to all of the previous limits, and that is the answer for this problem. The limit is 0. Let's solve the limit as x goes to infinity of x times the natural log of 1 plus 3 over x. First of all, is this an indeterminate form? Well, x itself is going to infinity, and that's being multiplied to the natural log of, well, 3 over x goes to 0, and 1 will remain 1, so this is 1 plus 0. This is infinity times the natural log of 1, which is infinity times 0. And yeah, that is an indeterminate form. What we will do is rewrite this limit as a fraction. It will also be an indeterminate form, and therefore we can apply L'Hopital's rule. What I'll do is write this as a fraction. I'll put this x into the denominator by making the exponent on it not positive 1, but negative 1. And I'll leave the natural log in the numerator. Furthermore, I'm going to write 3 over x as 3 times x to the negative 1. Like this. It'll be set up in a way that'll be easier to take the derivative. Now, is this also an indeterminate form? If you use this trick, it will be. But if you'd like to state what it is, the denominator goes to 0, and actually so does the numerator. This is an indeterminate form. It's of the form 0 over 0, which means L'Hopital's rule does apply. This is the limit as x goes to infinity of. The derivative of the numerator is 1 over 1 plus 3 times x to the negative 1. And then we multiply by the derivative of the inside part, which is minus 3x to the negative 2. This is all divided by the derivative of the denominator, which is negative x to the negative 2. So I took the derivative of the top and the bottom separately. Before going further, it'd be a good idea to simplify as much as possible. This negative and that negative cancel. This x to the negative 2 cancels with that x to the negative 2. This entire denominator is 1, so I don't even need to write it. There's a 3 left over that I'll put in the numerator here. If we simplify this whole thing, this is the limit as x goes to infinity of the single fraction, 3, divided by 1 plus, and we have 3x to the negative 1, which, if you'd like, you can put that back as a fraction. That's 3 over 1 plus 3 over x. This is no longer an indeterminate form. 3 is a constant, and the denominator approaches 1. And that's because 3 over x goes to 0 as x goes to infinity. So we can actually evaluate this limit. It's 3 divided by 1 plus 0, which is simply 3, and that is the answer to this problem. To solve this limit as x goes to infinity of this fraction, I'll note that we have an indeterminate form. The top is clearly going to infinity, and the denominator is going to minus infinity. So I'll state that this is an infinity over technically negative infinity, but that is an indeterminate form. So some care needs to be taken here. If you're looking at the limit as x approaches infinity of just the denominator, this thing, this is definitely negative infinity. And the reason is e to the x goes to infinity much faster than just 2x. But that all being said, this is an indeterminate form, and that means we can apply L'Hopital's rule. This is the limit as x goes to infinity of, the derivative of the top is 2x plus 4e to the 4x, and the derivative of the bottom is 2 minus e to the x. And the thing to point out is that this is, again, another indeterminate form. This is an infinity over negative infinity. And that means we can apply L'Hopital's rule again. This is the limit as x goes to infinity of, the derivative of the top is 2 plus 16e to the 4x divided by negative e to the x. And this is another infinity over infinity. So again, here we have infinity over really negative infinity. If we apply L'Hopital's rule again, this is the limit as x goes to infinity of, okay, we get 64 e to the 4x and still e to the negative x in the denominator. This is still an indeterminate form of infinity over infinity, and this will continue forever. So instead, let's simplify this. E to the 4x over e to the x is simply e to the 3x, And this negative you can actually remove from the limit since it is a constant. So this really equals negative the limit as x goes to infinity of 64 e to the 3x. In fact, you can actually remove the 64 from the limit as well, and I'll put that over here. This is negative 64, and then we have the limit as x goes to infinity of e to the 3x. Now, e to the 3x goes to infinity. It's being multiplied by negative 64. This thing is equal to negative infinity. Since that's what this limit is equal to, so are all the previous ones, including this first part here. This limit is negative infinity. In question 3, we're given a function f of x, told the domain is all real numbers, and also given its first and second derivative. Great. For part A, I want to figure out when the function f, the original function, is increasing, when is it decreasing, and then can we locate the x-coordinates of all the local maxes and mins? I'm going to note a couple of things. So I'll note that f is increasing when the derivative is positive. And here we're talking about on an interval. Also, f is decreasing when the derivative is negative. We can then use this information further to figure out if we have local maxes or mins. So to answer this question, I'm going to take the first derivative. I'm going to figure out where it is equal to 0, and then on a number line, label where it is positive and where it is negative. So I'm going to start by looking at the first derivative, which we're given, and I'm going to check to see where it is equal to 0. So I'm solving this. Where is 3x squared minus 24x plus 36, 0? I see I can factor a 3 out from this. We get x squared minus 8x plus 12 is 0. And I see this quadratic factors into two terms. We get an x and an x. They both have to be negative, and that would be negative 2 and negative 6. The product is positive 12. The sum is negative 8. This means the first derivative is 0 if x is 2, and if x is equal to 6, it is defined everywhere else. So I'm going to draw a number line. This is a number line for the first derivative. It's equal to 0 at 2 and at 6. What I want to figure out is here, here, and here is the derivative positive or negative. It must be one or the other. So if we're over here, I think an easy number to check in the derivative would be, for example, we could check 0, and you get 36. You get positive 36. So I know it's positive over here. A number that you could check in the derivative between 2 and 6 might be something like you could look at 3 and see what happens in the derivative itself. If you put 3 into this function, this is positive and this is negative, the whole result is going to be a negative number. I don't care what it is, but it's definitely negative. So we're negative here. And then if you check a number like maybe, 7, okay, it makes this positive and this positive. Therefore, the entire derivative is positive. So I know it's positive over here. The first derivative goes from positive to 0 to negative, then to 0 back to positive. So where is f increasing? So I'll say f is increasing on the intervals where the derivative is positive, which is here and here. So I'll say on the intervals from negative infinity up to and not including 2, and also from 6 to infinity. So here's part of our answer. Where is f decreasing? F is decreasing on the interval where the derivative is negative, which is here from 2 to 6. Okay, so we know this. And here we have two critical numbers. Are they local mins or local maxes? Well, by the first derivative test, the function is increasing and then it's decreasing. This must mean that x is equal to 2 is a local max. This must be a max. And if your function is decreasing and then increasing, this must be a min. I'll carefully state this on the next slide. I'll say by the first derivative test, as the derivative f prime changes from positive to negative at x is equal to 2, x equals 2 is a local max. And as f prime changes from negative to positive at x is equal to 6, x equals 6 is a local min. And again, the reason behind this is positive and negative is increasing to decreasing. So increasing to decreasing, there's a highest point. Here, negative to positive is decreasing to increasing, meaning there's a lowest point. This one's a max, and that one is a min. For part B, we're asked about concavity and also inflection points. I'm going to note that on an interval, we have the following. F is concave up when the second derivative is positive, and f is concave down when the second derivative is negative. And here's the formula for the second derivative. Just like in part A, I'm going to figure out where this is equal to 0 on a number line, and then determine where it is both positive and negative. So where does the second derivative equal 0? That's where 6x minus 24 is equal to 0, and that is where x is equal to 4. So on a number line, if you look at the second derivative, it is equal to 0 at 4. If you check a number to the left of 4, like let's say you looked at x is equal to 0, clearly you get a negative number. If you pick something that is greater than 4, like maybe 5, you definitely get a positive number. This completely determines where the function, the original function f, is concave down and concave up. So I'll note that off to the side here. We'll say f, the original function, is concave up on the interval from 4 to positive infinity. And f is concave down on the interval from negative infinity up to and not including 4. Again, that's where the second derivative is positive and where the second derivative is negative. Finally, what are the x values of any inflection points? X equals 4 is the location of an inflection point. And that's on the function f. And that's because there is a change in concavity. So this is definitely the location of an inflection point. The original function f goes from concave down to concave up. It is possible that your second derivative is equal to 0, yet there is no inflection point. For example, if it was positive 0, positive, that's concave up to concave up. That is no change in concavity. That did not happen in this example. We found where it was concave up. We found where the original function was concave down. And because there was a change, we can say x equals 4 is the location of an inflection point in f. And that's because there is a change in concavity. In question 4, part A, It says among all the pairs of positive numbers that add up to 100, can we find the pair that will have or yield the largest product? For this problem, I'm going to define a couple of variables, and I'll say, let's call them x and y, and I'll note that they are positive. We are told that they add up to 100, so with the variables I've defined, I can create this equation. And ultimately, I'd like to find the two numbers x and y that give the largest product. So the product, which I'll call my function p, is equal to x times y. I need to take the derivative of this function, set it equal to 0, and find any critical numbers. But it's of two variables, so I'm going to use this equation to create a function of a single variable. I'll do that by taking this equation and solving it for y. It's equal to 100 minus x. And I'll put that here. I now have p, the product, as a function of just x. In fact, if I multiply it out, we get 100x minus x squared. This is the function that I'd like to maximize. I'll do that by taking the derivative of this equation. The derivative of p is 100 minus 2x. To find any critical numbers, I'm going to see where this is equal to 0. That is where 100 is equal to 2x, or x is 50. And if x is equal to 50, and I put 50 here, I get that y is equal to 50 as well. Are these the two numbers that will yield the largest product for values that add to 100? To check this, just to be careful, I'm going to look at a number line for the function. We found its critical number was 50. That's where the derivative was equal to 0. For this to be the location of a max, the original function must be increasing and then decreasing. I can check to see if the derivative is positive or negative on either side of 50. For example, if you put, let's say, 49 in place of x, well, 100 minus, if you double 49, it's going to be less than 100. You get a positive number. So this is positive. If you put a number that's greater than 50 into the derivative, like 51, you'll get a negative number. Does this mean that we actually do have a largest or max value at 50? And it does. The original function is increasing and then decreasing, meaning there is a max at 50. So this is definitely the location of a max. And that's on the original function p of x. And therefore, we found two numbers that actually maximize this product function. Suppose we have 40 square meters of material to build a box with a square bottom and no top. I want to determine the dimensions of the box that will have the largest volume. So I'll try to draw a picture to represent this where, okay, we have a box and we know that the base is a square. So it looks something like this. And there is no top on the box. Okay, we got this thing. We need some variables. So I'll call this side x. So that's the length of this side here. And if the base is a square, then this side has length x2. But we're told nothing about the height. It could be something different. So I'll call that y. And our goal is to find the dimensions that will maximize, find the largest volume. So I have an equation for volume that is length times width times height. That's x times y. I'll write that as x squared y. This is the formula that I'd like to maximize. I'll do that by taking the derivative and finding critical numbers. But it's of two variables, so I have to find another equation that connects x's and y's. And that's where this 40 square meters of material will come into play. What is the surface area of this box? And I'll only consider one side of each piece just because that's the way you'd build this with this material. Well, the bottom has an area of x squared, so I'll write that down. And there's no top, so I'm not going to include this top part here. But there's a total of 4 sides. 1, 2, 3, and then this front, which is 4. There are 4 sides that have an area of x times y, so I'll put 4 times xy. This is the total surface area of this object, and that's equal to 40. This is all I need to solve this problem. I can solve this for y. It'll be in terms of x. I can put that here. That will allow me to continue with this problem. To solve for y, I'll subtract x squared and divide by 4x. So we have that 4xy is equal to 40 minus x squared. And if you divide by 4x, you get 40 minus x squared over 4x. This allows me to write my volume function as a function of x. It is x squared, and then y is 40 minus x squared all over 4x. Since I'm multiplying these two fractions together, I see that I can cancel this with one of those. I'll distribute this x to both terms and divide by 4. We get that the volume is equal to, if you multiply in x, you get 40x minus x cubed, all divided by 4. And if we break this up into two fractions, 4 goes into 40 10 times, making this 10x, minus, and 4 into this, I think the best I could write it would be 1/4 x cubed. My goal is to take this function and find its derivative and then locate any critical numbers. So continuing here, I'll take the derivative. The derivative is 10 minus 3/4 x squared. Okay, that's always defined, so I'll check to see where it's equal to 0. That is where 10 is equal to 3/4 x squared. So I just added this to the other side of the equation. I'll multiply by 4 and divide by 3. That's 40 over 3. And that is equal to x squared. Taking the square root of both sides, technically it will yield 2 answers, but x is supposed to be a positive value, so I'm going to say x is equal to the positive square root of 40/3. So here's my value of x, and this is in meters. Now, what is the corresponding value of y? I would take this value for x, and I would put it here to solve for my y value. I think I'll leave it unsimplified just because on this exam there will be no calculators allowed. So what is y? Y is equal to 40 minus this number squared, which is 40/3, all divided by 4 times that number, which is 40 root 40 over 3, and this is meters. So I have my x and I have my y. Again, not simplified, but this is definitely some number. So here are the dimensions. Does this actually, in fact, maximize the volume function, which is this thing here? To verify this, I'm going to look at the derivative of the volume function. On a number line, we figured out where it was equal to 0, and that was at the square root of 40/3, and that was meters. To the left, is it negative or positive? And to the right, is it negative or positive? All right, so here's my derivative function. If I put something closer to 0 in place of x, I'm going to get a positive number, positive 10. And if I put something really large in place of x, it's going to be negative. The derivative goes from a positive to a negative number. So it's positive and then negative. And that's enough to say that we have a max at x is equal to the square root of 40/3. Therefore, these are the dimensions that do in fact maximize the volume given this condition on the surface area. In question 5, part A, we're told that a particle moves with this acceleration, and we're also given its initial displacement and velocity. Can we actually find the function s of t that describes the position of this particle? For this problem, I'll note that if you have a position function and you take its derivative, well, that's equal to your velocity. And then if you take the derivative again, meaning you take the derivative of the velocity, this is your acceleration. we're going to do this process in reverse by using antiderivatives. We're given this, so in order to find the velocity, I'll find the antiderivative of the acceleration. So for this reason, v of t is equal to, all right, well, if a of t is 2t plus 1, it is t squared plus t. And the reason is if you take the derivative of this, you get your acceleration. We also have to add on an arbitrary constant, which I'll call c. To move forward in this process, I have to figure out what this constant is, and that's exactly why we're given this information. If you're looking to solve for this constant, we're going to use this piece of information here. Essentially, I'll put -6 in place of v of t and 0 in place of both of the t's. We get this. -6 is equal to 0 squared plus 0 plus c, or c is equal to -6. And we now have a complete velocity function, t squared plus t minus 6. If we're looking to get the position function, I'm now going to find the antiderivative of this function. The reason being, if you take the derivative of the position function, it gives you velocity. This means s of t is equal to 1/3 t cubed plus 1/2 t squared minus 6t, but we get, again, another arbitrary constant. I'll call it something different this time, so I'll call it d. To complete this problem, we have to know, well, what is d equal to? And that's why we're given this piece of information here. I'll put 4 in place of my position function. I'll put 0 in place of all of the t's, allowing me to solve for d. And I'll do that work over here. 4 is equal to 1/3 times 0 cubed plus 1/2 times 0 squared minus 6 times 0 plus d. No surprise that everything cancels except d. And this completes our function. I know that s of t is equal to, it's 1/3 t cubed plus 1/2 t squared minus 6t plus 4. If you want to check your work, you could take the derivative of this function to see if it equals your velocity function, and then take the derivative one more time to see if it equals 2t plus 1. It will for the numbers that we have in this problem, and so this is the final answer. We are told that an object was dropped, let go, from the top of a tower, and it hits the ground with this speed. Can we determine the height of the tower? And we're told to use this for acceleration due to gravity. A few things that we know are that for an object that's relatively close to the surface of the Earth, it will accelerate towards the ground at -32 feet per second squared. This allows us to set up a formula for the acceleration. A of t, the acceleration at any time, is constant. It's always -32. Furthermore, we're told the object was dropped or let go, which means we didn't give it any initial velocity other than 0. So we can say, if we're solving for a velocity function, the velocity at 0 is 0, and the units would be feet per second. We also know when the object hits the ground, it'll have this speed. I don't know what time that is. I'll call that time capital T for when it hits the ground, and it's going to be -136 feet per second. So negative will be downward, positive is upward. So maybe I'll note that capital T is the time when the object hits the ground. And we don't know what that is. So if we want to know the height of the tower, what I'm going to do is find a position function for this object. Meaning, since we know the acceleration, we can first figure out, well, what is the velocity function? That is the antiderivative of this equation, which is -32t plus an arbitrary constant c. We have to be able to solve for that arbitrary constant c, but that's where this piece of information comes in. The fact that we're told the initial velocity is 0. If we put 0 in place of v of t and 0 in place of t, it'll turn out that c is equal to 0. But just to write it out, the velocity is 0 at time equals 0, and therefore c is equal to 0. If we put this information together, we now have our velocity function. It's negative 32t. This will tell you the velocity at any time right up until we hit the ground. Now from here, if we know the velocity function, we can find the position function. So the position function, s of t, the height above the ground, is going to be the antiderivative of this equation, which is negative 32t squared over 2 plus an arbitrary constant, which I'll call d. It may be different than this number here. We can simplify this a little bit. We can say that s of t is equal to 2 goes into 32 16 times. So this is negative 16t squared plus d. S of t will represent the height of the object above the ground, meaning if you want to know the height of the tower, that's going to be the value of d, because if you put 0 in place of t, the only number left over is in fact d, the height at which it starts. To figure out this value for d, I think this is where this other piece of information will come into play. We have a formula for the velocity function, and we know the speed, the velocity actually, when it reaches the ground. That will allow us to solve for capital T. So what I'm going to do is I'm going to take the velocity function and I'm going to use this piece of information here to solve for the time it takes for the object to hit the ground. That means if I put negative 136 here, I have to put capital T here. So my equation for velocity becomes negative 136 is equal to negative 32t. Sorry, that was supposed to be capital T, the time when the object hits the ground. Now this will be in seconds. I'm going to divide both sides by 32. So t is equal to positive 136 over positive 32 seconds. Now what does that simplify to? So 136 divided by 32 is 4.25 seconds. That is how long it takes the object to hit the ground. At this time, if you put this time here, 4.25 seconds, what should S of t be equal to? Well, this is the time when the object is on the ground, so at this time, the height should be 0. I'll note that we can infer from this piece of information that if you put 4.25 seconds into the position function, you should get 0 back, 0 feet for the height. What I'll do is take this number, put it in place of t, I'll put 0 in place of s of t, and that will allow me to solve for d. So let's plug that information in. If s of t is 0, that means t must be 4.25. So if we want to solve for d, d is equal to, I will add this to the other side of the equation. D is equal to 16 times 4.25 squared, and this is feet. Now, this is the height that we're looking for. I don't have a calculator on me, so just to get an idea, 16 times 4.25 squared is exactly 289 feet. So that is the height of the tower. In question 6, part A, we're going to write the definite integral that represents the exact area bounded by the function g and the x-axis on the interval from 0 to 1. Then we will use these formulas to evaluate the limit. So to start with, the definite integral is the integral from 0 to 1. This is the smaller and larger x values of the interval. We then put the function g of x, which is 1 plus x minus x squared dx. The limit definition says this is the limit as n approaches infinity of the sum of I going from 1 to n of g of x sub I times delta x. And again, what this sum means is g times delta x is the area of a rectangle. You add them up, and then you let the number of rectangles go to infinity, ultimately resulting in the exact area. We have formulas for delta x and x sub I. Delta x is equal to b minus a over n, where the interval from a to b in this problem is 0 to 1. And therefore, delta x for this problem is 1 minus 0, which is 1 over n. X sub I is equal to our starting point a plus I times delta x. A is equal to 0. Delta x is 1 over n, so this equals I over n. I'm going to take this information, put it into this sum, and go from there. So this is the limit as n approaches infinity of the sum of I going from 1 to n of g of x sub I is 1 plus x sub I minus x sub I squared. That's 1 plus I over n minus I squared over n. And delta x is 1 over n. I'll multiply the 1 over n into the parentheses and eventually split this up into a sum of 3 different pieces. This is the limit as n approaches infinity of the sum of I going from 1 to n of 1 over n plus I over n squared minus I squared over n cubed. Since we're adding and subtracting things in here, I can split this up into 3 separate sums. That is the limit as n approaches infinity of the sum as I goes from 1 to n of 1 over n plus the sum as I goes from 1 to n of I over n squared minus the sum as I goes from 1 to n of I squared over n cubed. Anything within the sum that does not depend on I can be removed. I can factor out this 1 over n, leaving 1. I can factor out 1 over n squared, leaving I. And I can factor out 1 over n cubed, leaving I squared. This is the limit as n approaches infinity of 1 over n times the sum of I going from 1 to n of 1 plus 1 over n squared times the sum going from 1 to n of I minus 1 over n cubed times the sum going from 1 to n of I squared. I have a 1, an I, and an I squared. Therefore, I can replace each of those things using these formulas. This I'll replace with n. This I'll replace with n times n plus 1 over 2. And this I'll replace with n times n plus 1 times 2n plus 1 over 6. I'll do that on the next slide. We have that this is the limit as n approaches infinity of 1 over n times n plus 1 over n squared times n plus 1 all over 2 minus 1 over n cubed times n plus 1 times 2n plus 1 all over 6. This looks like a difficult limit, but I'm going to organize it in a way that we can look at each piece and quickly figure out what the limit should go to. For starters, 1 over n times n is n over n. This whole thing is just 1. So we have the limit as n approaches infinity of 1. Plus, here, I'm going to put the 1/2 first. And since I have 2 pieces here divided by n squared, I'll do n over n and n plus 1 over n. This becomes 1/2 times n over n times n plus 1 over n. Notice the denominator is still 2n squared, and the top is n times n plus 1. I'll do the same thing for the last piece. I'll put the 1/6 first, and I'll put each the n plus 1 and 2n plus 1 over n, like this. Notice that we still have n cubed times 6, 6n cubed. And then in the numerator, we have n times n plus 1 times 2n plus 1. These are equal to 1, so I'll cancel them. this is 1, plus 1/2 times just n plus 1 over n, minus 1 over 6 times n plus 1 over n, times 2n plus 1 over n. This is now written in a way where I know what's happening to each piece, and specifically this thing and this thing. As n goes to infinity, this thing goes to 1, because that's the ratio of the coefficients in front of the n's. And that is the same thing here. This goes to 1, again, because it's the ratio of the coefficients in front of n. This goes to 2, because the coefficients in front of n are 1 and 2. This entire limit is the following. It's 1 plus 1/2 times 1 minus 1/6 times 1 times 2. That's 1 plus 1/2 minus 2 over 6 is 1/3. So that's, if we have a single value, that is 7 over 6, and that's the value of the definite integral. For part B, we're going to express this definite integral as a limit of Riemann sums, and we'll use right endpoints on these subintervals. That's the definite integral from 2 to 5 of x divided by 1 plus x squared dx. Here the function that we're talking about, f of x, is x over 1 plus x squared. The interval from a to b that we're working on is from 2 to 5. This means that delta x is equal to 5 minus 2 over n, which is 3 over n. And x sub I is equal to our starting point plus I times delta x. And since the starting point is 2, and delta x is 3 over n, this is 2 plus 3i over n. This being the starting point, 3 over n is delta x multiplied by I. So to go to the actual Riemann sum, that's the limit as n goes to infinity of, if we're using right endpoints, we'll sum from 1 to n, and that is of f of x sub I times delta x. In place of these x's, I'll put x sub I, and in place of delta x, I'll put 3 over n. This is the limit as n approaches infinity of the sum as I goes from 1 to n of, okay, f of x sub I is 2 plus 3i over n divided by 1 plus, again, x sub I, which is 2 plus 3i over n squared, and this whole thing is multiplied by delta x, which is 3 over n. This problem says to not evaluate this limit, which is a great thing because this would be quite difficult, but this is what we're looking for here. This is the limit of Riemann sums with right endpoints.